thank you for joining us here today. We're really excited to have you all here. We're kicking off our second webinar today of our webinar series here at CLT Toolbox. Today we'll be covering the lateral stability and connection design of a post and beam office building. And today's presenter will be Adam Jones. So thank you everyone for being here. Let's get started. Before I take you through an introduction and introduce myself properly, I just wanted to take you through the agenda for today. So I'll introduce myself in a second, then I'll take you through some housekeeping, some new support options within the app, our latest release cycle, then we'll get to the design example by Adam, and at the very end, we'll have time for a Q&A before closing. So I'm Corey Jones. I'm the Customer Success Manager here at CLT Toolbox. I also happen to be the wife of the presenter today. So I joined the Toolbox team in the early days after my wedding with Adam in 2023. Before this, I was actually a ballet dancer, so it's a little bit different being a part of the mass timber industry, but I'm liking it equally as much. It's an incredible industry to be a part of. Here I'm pictured with the ladies at base camp, we call the office there, in Semarang, Indonesia, and they're part of our software team. Okay, so just some housekeeping. You'll find the previous webinar recordings now available on our community forum as pictured on the right here. So you can access all the recordings after our webinars there. For Q&A today, you'll see a button down below. It's not to be confused with the chat where everyone's saying hello and good morning to right now. There's a separate chat for Q&As. If you want to pop your questions in throughout the webinar, Adam will have time to respond to all those questions at the end. So go nuts, don't hold back. Support options in the app now. We just quickly wanted to take you through our new support options because our community forum is now directly within the app. So you can access your favorite mass timber topic discussions as well as discuss the CLT Toolbox calculators directly. We just wanted to let you know that it is actually right now a two-piece sign up, and we are working towards it being a one-piece sign up. So you'll only have to sign in once, but at the moment you do actually have to sign in twice. So just bear with us on that. That's going to be updated soon. We also wanted to let you know that you have now direct access to the team. So there's a chat as you see pictured here on the right. So you can put any screenshots you're having, any issues, any questions that you have, and it'll go directly to the team and the right person will get back in touch with you directly. Okay, our latest release that happened on February 25th, I just wanted to run through this quickly. This was our new steel beam and CLT calculator as pictured in the awesome GIF to the right here. We had updates to 6 Dowel calculators, which you'll see one in the webinar today. The community forum in the app, which I just discussed just a second ago. Our screw filtering feature now in the connections calculators. And we are now celebrating our awesome partners projects on the login page, which I think looks really awesome. I just wanted to note for the next month, all of our users will have free access to 2 of these calculators, which is the steel CLT beam connection detail and the wood steel wood loaded ankle dowel connections calculator. So one of the 6 dowel calculators will be free for the next month for all users. Of course, we wanted to thank our partners. We couldn't do this without them and from the support for the beginning, and it gives our users such an incredible experience having all of our partners on board. So we wanted to thank you heaps. Before we get started, I just wanted to mention why we're doing this webinar today and discuss quickly why architects love this building type so much. So obviously, aesthetically, mass timber is the most beautiful thing to look at when it's exposed. So that's a big one. The biophilic design, it's shown in studies that it increases productivity of its workers, reduces sick days, and all around well-being is just amplified. Of course, sustainability is a big one. We're growing our buildings now like we grow trees, which is really awesome. And I think one of the most popular ones is speed of construction, where this building's really heading in that direction. So we're going to get started now with our lateral stability and design connection design. So I'm going to pass over time. So I'm going to pass through. Hello, Adam.
Thank you, Corey, and good morning, everyone. And thank you so much for joining us today. So I'm going to get started and continue the presentation and the webinar series from what we started last month. So for those who haven't met me, I'm Adam. I'm the CEO of CLT Toolbox. I'm a structural engineer, used to work at WSP, XLM, Wood Solutions, and a few other places. So let's get into the webinar. So as a reminder, in the last webinar, if you want to go and check out the recording, we designed basic member design, so floors, beams, internal columns, external columns, and also a beam penetration check. So for today, as mentioned in the agenda, we're going to be focusing on lateral stability, and where we're going to start is on a diaphragm design of a simplified building like this. So if you look at the lateral stability, the way this system works is through vertical K-braces on the external parts of the building. You can see where the supports are with the core and the external K-bracing as well. You'll see that we're going to, in our calculator, use 4 separate rectangular diaphragm calculators. It's a bit of a unique workflow to what exists and focuses on, quick sizing at the early stage of design, where FEA might be suited for late, which I'll take you through. So firstly, the diaphragm design, you can see the loading from the wind, which I'll take you through in both directions, and that being taken from external workflows. All right, so let's look at the actual workflows of our new diaphragm design calculator. So firstly, like a lot of parts of CLT Toolbox, engineers do have existing workflows that can do parts of the design. In this case, it's using AS 1170 to work out the actual wind pressures and the actual loading on your actual lateral stability elements. So following that, you can take that into our rectangular diaphragm design. So as it says there, it is a rectangular assumption. It's not perfect. It's not going to get you everything like FEA, but it is filling a gap right now, which is where diaphragms can be a black box and unable to be designed at the early stage of projects. So the scope of this is going to be on preliminary estimations, diaphragm panel capacity and combined stiffness. We're going to look at the joint forces of our floor-to-floor connections, and then optional, you could take the panel and diaphragm stiffnesses and work interoperably with other FEM software if you wanted to do it like that. And then we're going to go into fixings design. So the point here as well, it is iterative. There are assumptions on fixings that impact the diaphragm. So you might need to jump in and out at this stage as we, over time, get the calculators speaking to each other directly. So taking another step, looking at the diaphragm calculator in terms of scope. So what we use is the deep beam girder analogy. This is used directly from the ProHoltz Volume 2 design guide. You can see here that you've got 2 simply supported collectors, and within that you've got the joints as well. And you can see constant shear flow between it. And as the force is developed at each joint, that is the corresponding shear flow developed at the joints. So following that, you've got a joint force distribution here. You can see the panel diaphragm based on that load angle, creating a tension force as well within the floor-to-floor connection. So you will have shear within the fastener in both directions as depicted by this image here. And then finally, we'll be checking the in-plane strength, and I'll double click on that more in a second. And then also relevant is the in-plane panel and diaphragm stiffness. So looking closer at the ProHoltz, it's actually volume 2, not volume 1, but you've got that model and you can do the lateral loading in both directions relative to the diaphragm in the calculator. When you're looking at the combined deflection and overall stiffness, there's 3 elements that we're going to look at. One is the panel bending deformation, which is covered, and the effective stiffness of all of our CLT suppliers on the platform. We'll be working dynamically to calculate this. And same with the panel shear deformation. So that's within the panel. And then the third element is the connection contribution. So you can see here, there's a few terms here, but the critical one that can vary and is specific to fastener producers is the slip modulus, which is K serviceability here. So the way we calculate that, we're going to show you 2 methods. One is through the current Eurocode, and it just has a formula based on the density of the timber and the diameter, but also the supplier ETAs is another option, which I'll take you through. And then finally, according to the latest research, we bring it all together and can work out the stiffness of the panel and the overall diaphragm, and I'll take you through that as well. When it comes to the in-plane strength of the actual diaphragm, there'll be 3 checks. So the in-plane bending design of the overall diaphragm, a tension and compression check with the girder analogy, and then the in-plane shear strength with the 3 failure mechanisms. All right, so with that said, that I think is important context for the diaphragm, which will hopefully let you follow along a little bit closer when I take you through the story of the design. So for us, we can do the different checks. We can design with Eurotech. We've got the Simpson guys. I think I saw them on the call as well. So Maddie, so we might give the Simpsons a run. And for the lamella width, that's going to be important for the in-plane strength. And that isn't always well, we don't hard code always the lamellar widths, and you might need to speak to suppliers from some of the data like that. So that'll be an input that we get from the Next Timber technical design guide that can be found in any supplier's design guides. So with that said, let's fire up the app. So you can see here our new login page. So it does toggle and just looks a little bit better and celebrates, again, our partners who've been working with us. All right, so give us a moment. I've got session expired because I was too long in the background waiting, but if that ever happens, you can just click return to homepage. All right, so for those new to it, it's a web-based app. A lot of you might be familiar with it by now if you're on this second webinar, but what we're focusing on here is the diaphragm design. So when you click a diaphragm, again, you've got the scope of a personal project or your enterprise. So we've got a lot of enterprise customers now, and you can do it as a shared project. So in this case, I'm going to go CLT Toolbox Design Team. We're going to choose the previous webinar. We're going to go webinar 2, Lateral Stability and Connections, and Diaphragm Design. So if we look back at this image, what we're designing here is remember there was 4 portions of 4 rectangles essentially that made up the diaphragm, and we're going to design this part of the building here. And you can see here, you've got 12-meter grids, so the panels spanning from left to right, and you can get 3 panels in at 2.67 meters at each grid line as well. So this is the section where we're going to look to design. So when you fire up the diaphragm calculator, you can see the dynamic image populated here on the right, and it is zoomable because the aspect ratios of diaphragms do change from time to time. For us, we're going to start with our Timberlink panel. So let's say we had a 220 panel working based on the preliminary member design you could follow the previous webinar. So you can, going through the different inputs, you've got the orientation, so the direction of the lamellas as well. So right now it is in the right direction along the actual length of the joints. So other inputs, so you got the length of the diaphragm. So we're 12 meters left to right, and we're 24 meters top to bottom. And with that, we can actually input our panel widths as well. So again, looks a bit hairy, but when you zoom in, you can start getting an understanding of how it's working. So we've got a half lap connection, and it does update based on the initial connection assumptions. So moving through, you've got the panel orientation. I mentioned that, so you can change it in the other direction. And then here is the part where it's just going to be iterative design without joint connections. So here we've got a spacing of 150 on our half lap joints. So next, as I mentioned, the connection data, the slip modulus does impact the overall stiffness of the diaphragm and individual panels. And you can either choose a user-defined slip modulus, you can choose the version based on Eurocode, as I mentioned, or you can choose the supplier version as well, and this is based on ETAs. So if we did go, say, for example, partially threaded screw and a 180 panel, but again, you can go back and forth to get that, and that'll get the overall stiffness, as I mentioned. So moving through, you got your design codes. So these are all default inputs because that's specific based on the method. An obvious question is, because we're designing from Australia, New Zealand, it is a performance-based design as well. So you are borrowing from Europe a lot in this case, hence we're explicitly just only having that as the option. So input forces, you can change the lateral force. So for us, we're going to go in the X direction. If I bring back this image, you can see here we're checking for this direction the force with 11.39 kilonewtons per meter ULS and a 7.59 SLS. So let's input our forces. Now this is going to test my memory of a goldfish, but for the sake of not jumping back and forth, let's just input them as our loading. And again, that can be taken from a different workflow outside of CLT Toolbox that most engineers are comfortable with. So strength parameters, we've got user defined right now, but we are working at hard coding it by suppliers, but some suppliers have gaps in this data. Hence, we'll just leave that as a user input here. So some of these can be found explicitly mentioned in the ProHoltz design guide, but I'd recommend speaking to your member supplier to work out what are the in-plane shear values and these 3 failure modes, which I'll also talk you through in a second. So the widths of the lamella data is also important. So again, taking that from the supplier design guide in this case, because again, it's not always explicitly consistent with every supplier, the widths, because they do vary at sometimes more than others. All right, so that's the lamellar width, also impacts the in-plane shear strength. And finally, you got your design data to Eurocode in this instance, and you can follow the more information to understand specifically what there is and get it more to the local context as best you can. So if I go through the calculations, you can see the scope of the check. So right now, as you'd expect, it's a big diaphragm working as one. So you wouldn't expect the utilization to be so high, but I'll follow through the calculations now. So firstly, the in-plane stiffness properties of the CLT. I mentioned before where that's relevant. Looking at the in-plane deflection. So again, the substitute deep beam girder analogy here from Proholtz Volume 2. Got the relevant section there. You can again see how the forces distribute and the overall assumption. So you've got the lateral load of the SLS, the effective stiffness. Next is the shear stiffness per fastener. So again, moving through here to calculate the case serviceability. Also relevant on the densities of the timber. So both of these being the same in this instance, the same panel, but in other instances, they might be two different. Yeah, moving through, you can see the equations. Again, not a black box. We follow it in full, but the equation that's familiar to you, what I showed before, is the panel stiffness, bending stiffness, shear deformation. And because it's a really deep beam, the shear deformation might actually be a bit more than, well, I probably originally expected when QAing this stuff. And then you've also got the connection contribution as well. So bring that all together, you've got your calculations, movement, your panel stiffness as well. So the individual panel by panel, but also the overall diaphragm stiffness. And again, this can potentially be taken into separate software if you wanted to, but at the very least, not a black box. You can actually do a rectangular design in here and maybe work hand in hand with FEM software, because yeah, it's important to understand how the diaphragm's working from first principles, which this can help, I guess, engineers understand. Moving through, you got your actions, your bending moment, the shear force. So a big bending moment's developed, but it's also a big capacity of a diaphragm. And then finally, the strength. So you can see here the different checks, in-plane bending design. So you can work out the stress here. So again, a really big moment, but a big diaphragm. You can see the analogy of how the forces interact. You've got tension at the joints as long as, in addition to sliding, so moments creating that force and the shear force in plane as well. So following this, you can see the forces developed along each axis, the axis being the bottom left-hand side of the diaphragm. That's the starting axis. Again, you sort of have to zoom in a bit to understand that. And then you got the forces per fastener. So the joint shear forces, kilonewtons per meter, which can then be taken into the floor-to-floor connections, which I'm about to show you and do a design for. And you can see the joint forces per fastener. So again, the loads developed for the fasteners, so easy transmission to the other calculators. And then following that, you got tension and compression strength within the diaphragm. So that's another check, which I opened with. And then, of course, the in-plane shear verification with 3 failure modes. So one, you're shearing off of the boards as per the Proholtz Volume 1 design guide. So I recommend, reading this side by side again, so you've got a dynamic calculation to the actual manuals that we're working with. Second, in the shearing off failure of glued surface of the joint. So you can see here the glued surface is working in torsion, hence the actual aspect ratio of the width I mentioned before being 115 mil, and taking that from the supplier design guide, impacting the torsional rigidity here, but also the number of glued joints, because each glued joint represents a torsional resistance to help with that check. And finally, the shearing off of the whole entire plate working together as one, and that's again following the Proholtz design guide. So it's a pretty comprehensive design. It's not a silver bullet where you might have penetrations, you have irregular diaphragms, but at least now at the start of projects where I think fasteners are assumed at really, generic, X screws per meter or a volume, and that lacks the efficiency. But as we actually go to understand deeper and deeper into the actual design, you can start finding that next levels of efficiency. So let's wait for it to print, because at the end of the day, it's the printing of the design report that comes together, and it takes a bit longer in our calculators based on the amount of data that's being saved. As you can imagine here, there's a fair bit going on in these calculations. So you'll also notice our print reports, they're always going to be the right same data as the calculation, so that won't change. But what will change is we are focusing on making them better, more aesthetic, and less space and stuff like that, and more organized. So you can expect that over time. All right, so that's a diaphragm. Next, we're going to go to the panel-to-panel connection. So like the diaphragm, we'll speak to the high level so everyone can follow along a little bit, and then we'll open up the calculations. So when it comes to screw design, we do have 4 methods available, and each has their own advantages and disadvantages, and it's important to understand the context of each. And, you know, it's not me specifying this is how you should do it in Australia. There's probably working committees to work through that, but I'll just talk through from best of my understanding. But I do also recommend anyone who's got an opinion on this to comment in the chat if they disagree with me, because we're an open book, or spur some sort of discussion. Obviously, probably something good for the community forum as well. But when we have the design methods available, firstly, you've got the Australian standards A1720. It's the most helpful for compliance. It is specified in the building code. However, you'll see not very sophisticated at all or as accurate as other methods. So it has that benefit, but that drawback. You got the current Eurocode option. This is the most mature in Europe. It's probably the most mature and well-used design code for screw design globally, probably in history. So you get benefits of that, but you're obviously going into performance-based design using another code. So thirdly, you've got the new Eurocode. That is the cutting edge version of Europe. So it doesn't have the widespread usage, but there will be extra checks in there, and that wasn't there previously. So it will be probably considered the best and most developed standard. Having said that, there are some other parts around the world where I hear things on screw design when it comes to things coming out of Canada and stuff. And then finally, you got the ETA specific to suppliers. So don't be mistaken. That's not just like a simple solve it once, use it once, check by us. We do that with each individual supplier. We go through about an 8-week process, or 8 to 12-week process, where a structural engineer and software developer produces specific to that supplier. So there's a lot of work that goes into this. And even though you're clicking buttons and changing codes, it looks like it's really easy, but there's a lot of logic behind each screw scenario to make it really advanced and easy for everyone using this software. So yeah, you can follow that in detail. So the joints we're going to look at is a floor-to-floor connection. So a bit more context here. You've usually got 3 options. So one is the half flat. It's got a good lateral transfer with interlocking panels here. There's less fasteners or less pieces than a spline joint to make that connection. There is extra machining. So you do have to CNC around the edges of the billet to create the panel, and then route on one side. So you do take a bit of timber away there, and you lose a bit of capacity with that. And the other one is fire is more compromising. So you're cutting to halfway through the panel. So for an FRL of, say, 120 minutes, the fire might reach the joint and compromise it sooner than the other connections. Secondly, you got the spline joint. It's versatile. It's less material wastage. It's pretty simple to build and install, to put together, but there's additional components. And again, feel free to, what's this like? It's almost like politics, talking about what joint everyone likes, different depending on where you are in the world. People got strong opinions on this. And then finally got the butt joint. So this is super easy. You just get a panel, a CNC 4 sides, and then you're done. Butt it together on site, and then do the screws at an angle working to get the joint. But it's the weakest joint type, and it's not. You may require additional joint protection because you could get gaps and things like that to deal with. So let's go into the actual design itself. So for us, we had a 220 mil CLT. We had forces developed in both directions, and then we can now go into the actual design. So let's get it up. You've got here, you got your connection design. You can see the different connection details. Corey mentioned this one's freely available on the free version at the moment. So you'll notice every release we are getting better at how we do our dynamic imagery and things like that. So I think you'll notice that that's quite advanced, but that's not what we're talking about today. So let's start with the half flat. Again, project management. We're going into the existing project. Let's go here, and we're doing our webinar 2, not the draft. We're doing this one and half lap connection 1. All right, and then fire it up. So as this is working, I'll take you through the dynamic images. So you've always got manual input on connections and member. It's always makes it easy to use. But we've also, the enterprise customers can add their own supplier. Hence our internal enterprise, we've got a lot of junk sort of additions there. So don't pay attention to that. But if you're an enterprise customer, you could basically add any supplier in the world, because not every supplier, you know, loves us. I guess like Store Enzo, they got Calculitis and probably might not partner with us anytime soon, but you could add any panel you want really if you wanted to. So let's go our Timberlink panel. You got a dynamic building of the section. So if you change the panel, it's going to dynamically update in both directions of the sections. So here you got two options. You can do a discrete floor type. It's a specific floor panel length that does take into account the edge distance requirements. An alternative is to use a continuous design. So this design's per meter, and because of that, it does account for the decimal of screws rather than a discrete number of screws, and you get a bit of extra capacity. So I'll keep it like this in this view for the next part. So next you got your screw supplier. So again, you can choose your screw here, and with that, you've got the screw types, you've got warnings, so it's telling you to use a longer screw, obviously. So if we go through here, you'll be able to actually dynamically build up the screw and so forth. So quite straightforward to click around and understand each part of the supply chain as well. So here's all the Simpson guys, more information here, and you can understand a bit about the service classes from the European context as well. But again, you can always just keep changing, you know, understanding, having that versatility from a screw design point of view can be the best option for a client as well, and having that power. So there's a lot of flexibility just in this logic. The second lot of flexibility is around the analytical methods. So currently you have current Eurocode, AS1720 and draft Eurocode as your fundamental methods. But for example, the current Eurocode, you got the ability to design it to the current Eurocode, but get your capacities according to the ETA. So let's start there, and I'll do some optimization in a little bit. So geometries, got your orientation. We can change our spacings, get it closer. Well, we haven't put in our loads yet. I'll put in our loads. So we've got 8.5 and 7.5. You can see we've got our shear capacity failing now at 151%. You've obviously got this case, you can increase a 6mm screw, get a 8mm screw potentially to work, which we did in that instance, or you can change the spacing. But at least you've got that option. And you know, one recommendation is probably fix the screw type and have it a consistent screw across the project, and then update the spacings might be easiest from a complexity on site. So there's all those smarts with experience you can overlay in addition to using CLT Toolbox. So you got your design data here. You know, again, more information, what does pre-drilling do? You got wood splitting. It helps with a few bunch of things. And then you can start doing the checks. So again, the geometry check. So this is based on the ETA, and let's look at the difference between methods. Actually, I'm jumping around a bit, but let's look at the capacity, and then we'll look at the difference between each method. So I'll mention through geometries. Now you got your lateral capacity. So go through each check in detail and all reference for the specific clauses. And as I said, we've had a team, probably like on average 6 or 7 people for like 18 months now on just screw design. So we keep going deeper and deeper to providing more advanced software for engineers. And the reason why it's important for advanced software is because, you know, if through a click of a button, you can understand the design better and get 10% saving on your capacity. That might be the difference between, for the client, of $20,000 right there. So, you know, building one spreadsheet for one method, not sophisticated, might cost more money, I guess, than actually having the advanced tooling solution to get what's best for the client. All right, so I've done it based on current Eurocode or the ETA. If you click more information, you've again got some extra information. So what is AS1720, current Eurocode, inclined screws, impact of that, spacings and edge distances. You can see here, for example, spacings, we say it's best to follow the ETAs because that is specific based from supplier to supplier. But for the sake of it, let's just change to the compliance method. So let's go to AS1720 and see what happens. So you can again change back to AS1720, really simple geometry checks in this case. You can see our capacity is working at 42%. So if you did it just on AS1720, you'd be working easier and you'd get less space, less screws for the project, but that's obviously not best based on the latest cutting edge design methods. From a lateral capacity point of view, again, really simple tables taken from the AS1720 approach. But we do have the option, and again, this is different. There's different schools of thought on this, but we do give the ability to work out the screw capacity based on the ETA and then use AS1720 for your K factors. And the K factors take into account some of the implications of local timber species. So yeah, there's a lot of layers when it comes to screw design. But for us, let's just go back to the Eurocode if we wanted to design it like that. We're working at 87%. Let's save it, and then I'll go back to the project level. So that's also important. Remember to save your calculators on CLT Toolbox because it doesn't save, it doesn't auto save. So you need to create it yourself essentially. So you can always go here. You can add your calculators from this view. Click that and add it to the group. So we're at webinar 2. We'll call it spline L1, 2. That is just a pretty random name, but that's okay. But yeah, so you can see here the project team, you've got the different people in it. I put a chat in there, but no one responded to me on the team, unfortunately. But you can also assign tasks and calculators, a few things in the project management, which we're also working on. But I added the calculator to this grouping here, so let's open that up. So again, from an engineering point of view, you could, at the very start of a project, have the half lap joint available and the spline joint available at the very start and take that to the client and have different fixings options, speak to different fixing suppliers. And again, that ability to get that speed of construction. But let's just fire through this. Spline thicknesses, you got your densities, your screw data. Well, you probably don't need, let's get our screw. Again, you can work through quickly. Follows the same process of the ETAs. You can input your forces, go back to the design data and see all the calculations. So through here, you can see here the geometry checks based on the distance between the screw loaded edge and the spline. So with that, you can start getting the actual geometry checks right from a spline joint. So again, I'm going quick mode here. I think I need to move it the other way. Oh, I've got it working then. So with the calculations, you can really configure your spline joint really quickly and easily to get the calculations and follow it all through. But logic follows the similar process of just not being a black box. All right. So it's designed a half lap, designed a diaphragm. Next, we're going to look at another advanced calculation workflow, which can work outside with other software examples out there, your Microstand, Spacecast, Luba, whatever it might be. So we're going to be doing a lateral K-brace design. So step 1 is the analysis. Currently, this is done outside of CLT Toolbox. Every engineer does, we assume, would have a workflow since uni to design a vertical bracing element like that. And with that, we can take the forces into CLT Toolbox and do a member design and check for tension and compression within the member. And thirdly, we can do the connection design, so large dowels or bolts. And the reason this is iterative is because you might do a member design that works, but the actual geometry checks to get the bolts right is one of the interesting things about the detailing here. And it does take a bit of energy, but as you do it, you might actually have a bigger section size than you would for the member, hence the iterative process that you might require. All right, so bracing, we can do the initial calcs. Again, from an early stage project, you could do this relatively by hands, get the elevation, work out the forces based on the wind loads, run it through an analysis to work out the forces, and the governing force being the bottom element of the K-brace, as you can see here. And you'll have the tension, worst case tension, worst case compression checked separately. So for us, if we're designing the critical K-brace members, for our worked example, we worked out with something like this. So you've got critical for compression, 175 kilonewtons, critical for tension, 68 kilonewtons, with a 5.6 meter lateral bracing. So for this, back to new calculator, excuse me, go to the timber member design. We're not in personal, we're an existing project. Back to our webinar example, save it to this grouping, bracing, L1, A, wherever it might be. All right, so I'll talk about this calculator at the higher level because it can be useful in a lot of different contexts. So you can see here, a lot of this is just for illustration purposes. So you've got a dynamic view. We can get our bracing element. You can see the forces within the timber member. And for us, we can get our correct bracing lengths. And for us, instantaneous loads because it's the wind. This here, it's just a section. As we get tapered beams, that'd be more interesting, but it just shows you the section of analysis that we're looking at because it's just a input forces design. So like always, you can manual input for us. So 24H, and you might do, say, let's just go a more efficient size because aesthetically you might match the dimensions here to be the same as the beam and column. The other disclaimer here is we aren't doing fire design, so fire might govern the design of this as well, and then you'd actually input your post-fire section dimensions potentially. But let's just put a member in that's efficient. So for design action effect, you've got bending, shear force, and axial as options in this calculator. So you can see all the checks here for really quick checking based on all the forces, and it's a very long calculation list. But for us, if you just simply put this is 0, this is 0, and it'll start hiding the irrelevant sections. So for us, 0, 0, 0, 165 kilonewtons compression. For the Eurocode, you got a compression check and a stability check. And then you got your design data as well. So KC, service class, effective length factor. You can follow the calculations, so your material properties, and again, the design check relevant here. It's quite dynamic. So when you turn things back on, it'll run all those calculations based on what you're in. So some calculations you might consider if you've got an eccentricity and you want to add some bending moment into this calculator in addition to the pure force, you could do something like that pretty easily. But for us, we've got a quite straightforward check here. You can see the checks here from a dynamic image point of view and how it's all working. So let's save our calculator, and that's the basic member design. So a pretty straightforward check, which brings us into something a bit more technical, which is the large dowel and bolt design. So for us, we can look at a connection detail like this. You've got a force acting at an angle potentially on the timber member here, and you've got force running parallel to the member here. So you got a dowel and bolt calculator here. The scope of the calculator I'm about to show you can handle that. So you can see the design that we're trying to do. We're not up to questions yet. All right, so for this, luckily we did run some major upgrades to our large dowels and bolts calculators, and we're about to go through another version of this actually. So you can go through here. You got the wood, steel, wood parallel to grain is the scenario that we've got in this case. So again, let's just get our project up group. Bracing connection 1. Now it is finicky, this calculator, from a detailing point of view. So as I do it, I'll do my best to actually get the sections right, but it might take 5 or 6 minutes clicking around at this stage to get the dimensioning perfect for the geometry check. So that's something you'll notice in the app at the moment, but we're going to put some additional smart logic of dowel arrangements in coming releases. So for a negative, You got your compression load here, so put negative for it to be compression, and some of the checks do update based on that. So if that's a positive, so for our tension, if that's a tension check, you've got your group tear out resistance, net tension resistance. So again, there are additional logics that meets the eye that's going on in the software sometimes. But for us, let's input our dimensions. So configuration parameters, we'll probably come back to that in a second, but let's just go, for example, 3x4 rows. You can see 3x4 rows, you got both cross sections and how the dimensions work. So currently it's input as a 240x420, which was different to what we designed. So let's go wood side member. So let's just try what we did before. I think we had 180x250. And you're probably going to see, yep, some funky stuff there. So we'll work on that in a second. Fastener properties, you can input your fastener grades. So M12, it automatically calculating the diameter of the washer type that's required. And again, your design data. So as you'd expect, dimension check currently not working because we're technically out of the timber member. So this is where I'll go. All right, so you can see here, if you're trying to get the dimensions right here, you can click the more information to understand what's going on. So you can see here, A3T is the left-hand side loaded edge. What we're trying to do is you can see A4T. So right now it's 110 millimeters. So when we actually bring it back in line a little bit, we can start getting our design in line as much as we can. But you know, so as you keep doing this, we've now got our dimension check working actually, which is great. So you can see, go through here, we've got all the checks. It'll tell you what is not working. So you can easily click the more information and play around with this until you get it working acceptable. And as I showed you then, to get this working, the dimensions right from the number of rows and number of fasteners, including the washer heads, that might be the thing that governs the design. So you know, it is important, I guess, to toggle this, play around, get the connection detailing right, and then that might actually configure the moment design. So right now, what are we on? We're on the current Eurocode, and you can see all the calculations in detail. So rope effects, the value of fasteners, effective number of fasteners. You can see the failure modes in the timber or in the steel. So that does provide you a workflow with CLT Toolbox for a seismic design. We don't explicitly do seismic design, but at least you can see where the failure is and if it's ductile or brittle. Over time, we're going to have the ability to just toggle on seismic and input overstrength factors and everything like that. But yeah, you can quite simply, again, do your different design codes. You've got current Eurocode, draft Eurocode A1720, which is you know, not the greatest, but you also have NZSA 1720 and draft Eurocode. So similar methods before, draft Eurocode now, including plug shear resistance, brittle failure modes, net tension resistance, everything like that. So let's just see, based on the summary here, we changed the method and now we're failing in yielding resistance. Yeah, so we got M14 working, but now the dimension check's failing. So what's failing? Check spacing. You can see here the A4TC, loaded edge member distance is A4T. Go up to A4T. This is referring to this, and you can play around with that and, you know, get it working. And you probably need to get a deeper timber section. So again, play around with it and you can start getting the sections. For a bit of fun, we've also got a 3D view. That's more of a look what's coming, and as we get more complex detailed connections, you can get that. So we've actually got the washers and everything like that built in now. All right, so back to 2D view, hit save. Hopefully you can screenshot this and send it to your drafting team as well to actually create the drawing. So if anyone's used our dowels before, I think this represents a major upgrade compared to what it was in many ways. So, and then you can always print. Always, you can print at the project level as well. I could have done that. So I could have gone back and printed like 10 pages at once for the PDF. But in this case, we'll just print calculator by calculator. Again, bracing connection. A PDF should be a bit cleaner. all in detail. So hopefully it's really built these PDFs in the mind of a certifier who doesn't understand timber, hence we provide the detail. That's a good thing, but the negative thing is it's a really long PDF report. So another thing I think I mentioned in the last webinar is one-page PDFs. So you've got that option as well. So with that said, hopefully that gives good detail for everyone. I'm going to stop sharing and invite Corey back online for some questions. So thank you.
Thank you, Anna. We've got some awesome questions coming in here. So if you want to help me spotlight them, we'll start off with the first one. Can you show us the new report style at all? When can we expect it? It's from Anonymous.
Yeah, I can. I'm just going to open up Figma. Can everyone just hold off for just 2 seconds, because it'll take me 2 seconds and it is important. That was quicker than I thought.
Everyone speak amongst yourselves.
All right, so I'm going to just share my screen. So you can see here the new report's going to work like this. You can see where we're going to is PDF import export to Excel as well. So that'll just be a CSV file with just the data. And in this, you can turn on or off each toggle. So geometry checks, whatever it might be, but you also have a one-page PDF and you can toggle it through here. We are also working on the ability to comment a layer on top of this. So how can you actually provide commentary on each calculator? We're working on something through that. So that's how that'll work. And then the actual design of the PDF, this will be the one-page PDF report. So thanks to GHD, they emailed us a suggestion, hey, can we put our logos there? So hence, we'll have the enterprise customers logo here, an image of the connection detail of the image, and then for the utilization check, so this will just be all compressed into one page. So you can see here, this is it's a bit of a process we go through before we decide it, but this is pretty deep in development. So I'm glad someone asked that question.
Awesome. Next question we have from Anonymous also is there a way to see the imagery more easily while making changes instead of needing to scroll up and down?
Yeah, that's a really good point. So at this stage, there's not, but it is something that's come up a lot. Very early days, we had split screen function in the app. So you could click a button and it would separate the input so you could toggle in two parts. It was just really unstable when we did it. It just made the app a little bit unstable. So we're going to implement something like that again. Maybe we can do like utilization checks follow you everywhere you go, and hence as you're doing the inputs, you can see the utilization check. I'm not sure if it's an anonymous person, but if maybe put a thumbs up if you wanted to and say, would that help if you just had a utilization ratios on the right-hand side of the screen where the inputs are, so you can see if you're making it work or not. But yeah, we're aware that's a challenge, but yeah, feel free to, if you got any thoughts, you can let us know as well.
Great. Awesome question. And we'll have time for a couple more, so pop them in the chat if you have any. Otherwise, there's two remaining. We have one that's, what about the ability for multiple plates and moment connections in design?
Yeah, it's also a really good question. So that is the next iteration of our Dowel calculators. So at the moment, you got 17 scenarios, like I mentioned before, internal plates, external plates, all simple connections, but we are grouping it into one, stacking them on top of each other for powerful Dowel calculators where you can add moments. And yeah, this is pretty late stage development as well. I could demo like the Excel prototype that we've got, and that'll give you the internal number of internal plates and external plates as well. So that's, if you've used Deliverable before, sort of, I think, well, our team thinks it's going past that, but that's what our team thinks. But yeah, hopefully that answers that question.
And our final question for today is maybe relevant for later, they said, but I'm wondering if you can include seismic design at all.
Yeah, great question as well. So that's something I sort of covered at the end, but at the moment you can just see the failure modes quite clearly in the calculations to see if it's from steel or timber, or if it's brittle. So you can, I guess, optimize from that sense, but the actual seismic check isn't included. It won't be too hard for us to actually include it because all the hard part's done. We just need to actually just layer some logic on top of it so you can toggle for seismic. So yeah, but you'd input your factorized design loads for your seismic design into the app.
All right, awesome. If there aren't any more questions today, I've just got a couple slides for closing. Thank you everyone so much for being here. We really appreciate sharing with you all. So it's really awesome. I just wanted to bring your attention to our next webinar, which is coming up April 2nd. And more specifically within the webinar, we'll be covering CLT floor to beam detail design, CLT floor to steel beam detail design, custom beam to column connection, GLT beam notch, and there'll be a CLT floor penetration sneak peek. Again, we've got our EU UK being presented by Marco, probably when our time zone's asleep, and Adam will be presenting for ANZ. I just wanted to note that if you wanted to book a demo today, we will be offering discounted licenses off the back of our webinar series. So I've put my email in the chat as well as a link. You can either get in touch with me directly or go through the usual book a demo link. Just want to note as well, for our demos, we can demo specific to any projects that you currently have. So just be in touch about that and we can collaborate and make sure it's the best demo for you. So yeah, from Adam and I and from the team at CLT Toolbox, we wanted to thank you for being here today. We hope to see you as numbers at the next webinar in April. And it's been really great. And thank you, Adam, for the presentation. All right.
Thanks, everyone. Have a great day.
Bye, everyone. Have an awesome day.
Bye-bye.